Hey AP Chem, welcome back to Titrations Continued. So now that we have seen the titration setup, I want to go through and talk you through a little bit of vocabulary and also revisit some math within solutions inside the context of titration. So let's start with the vocabulary. Okay, so there's a couple terms that are used specifically with titrations, and we talked about them through our experimental setup. We just didn't put the technical term with what we were describing. So that's what I want to do now. I want to fit the technical terms with what we saw in that titration setup. Okay, so this is a type of volumetric analysis. All that means is that you have a specific volume of a specific solution, and you are using some type of technique to analyze what's in it and how much is there. So titration is one method of a volumetric analysis. Titration itself is exactly what you saw in the setup for the lab that we did today. So it involves delivery of a measured volume of solution. That's from a burette. Usually that is what you know the concentration of, and you're putting that into a solution containing the substance being analyzed. So that uses two words there, titrant and analyte. The titrant is the thing that you know about. You measured out the volume. You made the solution up. That is your standard solution. So you know the concentration. By the end of the experiment, you're going to know the volume. You know everything about it. That's the titrant. The analyte is the thing you don't know about. Usually you know the volume, because if we're going to go test a river, you're going to measure out a specific amount of the river into your beaker, but you don't know the concentration of the thing you're studying. So the analyte is the thing that has the unknown concentration. Now, indicator we talked about. The indicator is that molecule that has two different forms, an acidic form that has the H plus attached, and the basic form that has the H plus dissociated. And the two forms of that thing are two different colors. That's what we call an indicator. Just to give you an idea, for example, if HCl was our indicator, which HCl is not an indicator, but let's pretend it is. If you had HCl, the molecule, that would be your acidic form, because you have the H plus attached. If you have the H plus dissociated and you just have the Cl minus, that's your basic form, because the H plus has dissociated and is floating off by itself somewhere. So these two forms, if these two forms were different colors, then HCl could be used as an indicator. Now, indicators are never strong acids or strong bases. They're always really, 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 really weak acids and bases, but you get the idea. So two different forms, H plus on, H plus off, two different colors, becomes pretty useful for us. And now we have these other two terms that are really close together. One is called the equivalence point. You might hear it called the stoichiometric point, but equivalence point is more common. And then the other one is called the end point. So these two are really similar definitions because they happen around a very similar time. Sometimes they happen at the same time, but their definition is technically just a little bit different, so you should be able to differentiate between the two. So the equivalence point is where enough titrant has been added that you exactly match how much analyte is there. So for example, let's say we're talking about the lab that we did today, right? So you have acetic acid. I'm just going to put AA for acetic acid. So let's say we start with 3 moles of acetic acid in our beaker, right? And then we're dropping in NaOH. So as we drop in 1 drop of NaOH, it's going to match with our acetic acid, and they're going to neutralize with each other, right? Let me just write that reaction out. We're going to talk about neutralization here in just a second. So you have HC2H3O2 plus NaOH. Okay, so it's a double replacement reaction where the H and the OH match up and you get water. And then the salt, the ions, the anion and the cation match up and you get NaC2H3O2. So if I put 1 mole of NaOH in there, I'm going to neutralize 1 of my 3 moles of acetic acid. So there's no more NaOH, but there's still 2 more moles of acetic acid. So then we put in another drop of NaOH. Okay, again, they're going to react, double replacement reaction, and neutralize each other. So I have no NaOH left in there because all of it has reacted with the acetic acid, but I still have 1 mole of acetic acid in there. So if I put my final drop of NaOH in there, that reacts with my final mole of acetic acid. And now I have no more NaOH because it's all reacted with the acetic acid. I have no more acetic acid. It has all reacted with the NaOH. So I have no more reactants left. I have only water and salt. This is the equivalence point. Enough titrant, NaOH, has been added to react exactly with the analyte, acetic acid. They have been added in equal amounts. They have completely reacted together. I no longer have either one of them. I have completely a complete set of products now. That is the equivalence point. And now at this point, if I add 1 more drop of NaOH, then my indicator flips from that acidic form to the basic form, turns from colorless to pink. Now the endpoint is a very similar point because the endpoint is where the indicator changes color. Now we're going to design our experiment so that our endpoint matches our equivalence point, but they don't always match up. If there's hundreds of indicators out there and each one changes at a different place in this H plus to OH minus, H plus to OH minus ratio. They all change at a different point in that H plus to OH ratio. And so your endpoint and your equivalence point are not always the same. Now ours was because we picked an indicator to change at the right point for our reaction. And that's what you want to try and do for titrations. When we get into acids and bases, we'll talk about how to pick an indicator. But for now, I'll just tell you the right indicator to use. So equivalence point is where acid equals base. You have only water and salt left. Endpoint is where the color of your indicator changes. Okay. So when you're doing a titration, we talked about this. The data that you need to write down includes things about your titrant and things about your analyte. So you should know for your titrant, you should know the concentration of your titrant because that's your standard. You should also know the volume of the titrant that you end, but no, you won't know that until the end of the reaction, right? We didn't know at the beginning of the reaction how much NaOH we were going to add. We didn't know that until the very end of the reaction when we went back and looked at our burette and then figured out, okay, how much of the titrant did I actually add in this. The analyte, you're going to know the volume because you choose it, right? If you're going to go analyze a river, you're going to take out a specific amount of that river and you're going to know how much you took out so that you can find that mole to volume ratio, which we call molarity. You don't know concentration of your analyte because that's what you're doing the reaction to figure out. So that is what you are finding. Now, one other thing about the titration setup, most of the time you're going to see the analyte in the beaker, in the titrant in the burette, but that's not always the case. For example, if we mix up our titrant and it doesn't dissolve super well and it still has some chunks in it, well, we're not going to put that in our burette because it's going to clog up our burette and then our burette won't work anymore. So sometimes we have reason to flip the analyte and the titrant. So you do have to be careful to read your directions or read your instructions or read the context and figure out which one is which. Okay, so in order to do an effective titration, in order to analyze a solution with a titration, you have to know the reaction. The equivalence point must be marked accurately. And this is what we talked about when we were doing our titration. Remember, we did that first one that we called quick and dirty. We just did it quickly to mark the ballpark area. And then we were going to go back and do a second one where you get close to the equivalence point. And then you add in base drop by drop by drop so that you get a really accurate equivalence point marked. If you're not accurate, you're going to have error on one side or another, and you're not going to get a very good answer out. And then the volume of titrant, you have to know the volume, and you actually have to know the concentration as well. Okay, now not all titrations are acid-base. We use the term neutralization anytime you're adding an acid to a base. If you have an acid plus a base reacting together, it's usually a double replacement reaction. So we might call it that, but more commonly we'll call it a neutralization reaction. If you use, sometimes your analyte is a weak acid. It can also be a strong acid. The titrant is usually always a strong base because otherwise it takes you forever to get to your equivalence point, especially if you don't know what's in the water you're analyzing. You can always switch it later, but it's usually faster. Or vice versa. Sometimes what's in your solution is a weak base, and then the titrant is probably going to be a strong acid just because it gets you to the end point faster. Phenolphthalein, you'll see this one a lot. This one's super common. It's used usually with strong acid, strong bases. And again, once we get to the acid and base chapter, we'll kind of talk about why that is. It actually has kind of a funny range where it changes color. But once we get through equilibrium and you know more about acids and bases, you'll know why phenolphthalein's kind of interesting. But it's super common to use. It's really safe. It's very cheap. It's very common. And so it's used with strong acid, strong base titrations a lot. And then if you hear this term, standardizing the solution, you know that what you're trying to do is accurately determine the concentration. So you could say, I'm doing a titration to figure out the concentration of the solution. Or you could say, I'm standardizing the solution. Both of those things mean the same thing. Oh my goodness. Okay, we talked about Indicators, we talked about phenolphthalein. We talked about how the color changes the endpoint. Okay, so now I want to get a little bit into the math. Let's back up a little bit and do some of this straightforward math here. Now, this again, the math behind this is just dimensional analysis. That's all it is. And usually it's dimensional analysis within our very well marked mole hole, right? Which is this. Okay, usually it's within that. But they're throwing a concept at you at the same time. So the math seems to get a little bit more tricky than just the stoichiometry that's in chapter 3, because you have to deal with this context at the same time. But remember, it's all dimensional analysis. You can, if you feel stuck, just take a deep breath, analyze what do you have, and then see if you can line the units up to reduce out and end up with the unit that you want. If you feel stuck, evaluate your starting amounts and then play with it like it's a puzzle. And sometimes you can figure the math out before you actually can figure the concept out. And then sometimes it's the other way around. So let's look at some of the simple, straightforward problems before we get into some of the more complicated problems. Okay, so what volume of a 0.1 molar HCl solution is needed to neutralize 25 milliliters of 0.350 molar NaOH? Okay, so again, we're going to this point of neutralization, and at this point of neutralization, you have to know a concept. You have to know that when things are perfectly neutralized, the moles of acid are going to be equal to the moles of base. So if we can figure out one of these, then we know the other one. The first thing you should do is you should write out a reaction and balance it. All right, so I have 25 milliliters, 0.025 liters of NaOH. And then they also tell me I have 0.350 moles per liter of NaOH. So how many moles do I have? .025 times, what is it, 0.35? 0.00875. Oh no. Moles of NaOH. Okay, so at my, that's how many moles of base I have. Now, if I have that many moles of base, let's figure out how many moles of HCl I'm going to need. And it's a 1-to-1 reaction because we balanced the equation. And once I'm in moles of HCl, then I can use this 0.1 moles. So I want to get from moles to liter. So the 0.1 goes on the bottom. These are both for HCl. Okay, so my answer divided by 0.1. .00875 liters of HCl. There you go. So notice, here's what we did. If we go back over to our mole hole and kind of look at what we did, they started us in volume of one thing, volume of our base. We went to moles of our base, moles of our acid, And then we went back to liters of our acid. So again, it's just dimensional analysis. You're using the mole just like normal. It's just within a context, so it makes it a little bit more tricky. And you do have to know about your context in order to answer this question. All right, this would be a good place to pause and see if you can beat me. One note here is that it's not a neutralization reaction, it's a precipitation reaction, but it's still done with titration, and so the idea is completely the same. You are adding two things together, reacting them until they're both gone from the solution. So pause it, see if you can beat me. All right, here's my reaction. The quantity of Cl in a water supply, Cl minus, is determined by titrating the sample with Ag plus. All right. How many grams of chlorine in a sample of water if 20.2 milliliters, 0.1 molar silver is required to react with all the chloride ions in the sample? All right. So if we look at our mole hole, oops, I did that backwards. And then we have the opposite for the other thing. Okay, I am given volume of silver. I want to get to moles of silver, moles of chlorine, and then I'm going to go to grams of chlorine. All right, let's see if we can do this. So 0.0202 liters times liters per mole, and this is all for silver. And now I want to get out of silver into chloride. It's a 1-to-1. And then I want to get out of chloride into grams. Okay, and that I need the molar mass off the periodic table, which I think is 3545. Let's find out. Oh, there we go. Yeah, 3545. Okay, so I have 0.0202 times 0.1 times 3545. 0.0202 times 0.1 would give us 0.00202 times 35.45 equals 0.071609. Grams of chlorine. Nice. Okay, if the sample has a mass of 10 grams, what percent chlorine does it contain? So this is throwback to mass percent. So part over whole. Our part is the chloride ion. Our whole is 10 grams, so not much. So divided by 10 times 100. .716%. Sample is 0.716% chloride ion. It's good practice to start doing like tens and hundreds and 0.1s in your head, so you get comfortable with that math, since on the multiple choice, that's a favorite number, multiples of 10, to force you to use without a calculator. Okay. I feel like this would be a good one for us to do together. Let me make it blue so I remember. And then we'll go down to a couple questions with specifically titration math. All right, one note before we get going on the titration math. Again, if you get stuck, a really good thing to start doing from the beginning is to write down all the components in the solution and then figure out what's actually part of the reaction. As we get more advanced, especially once we get into the acid-base chapter, they're going to give you things that aren't actually part of the reaction. And that's part of the evaluation you're going to have to do, is figure out what's part of this reaction and what's not, and what actually matters. So it's a good habit to get into as you go, to just start doing that from the beginning. All right. This would be a good time to pause, see if you can beat me to the answer. Oh, they're giving us a limiting reactant reaction here. So HNO3 KOH. It's going to give me KNO3 plus H2O. And I have 0.028 liters of HNO3. I have 0.25 moles per liter of HNO3. And so I can actually do that automatically and get myself to moles of both of these and just deal with this whole problem in moles. I'm probably going to do that. So this is what I have initially. And this is for KOH. Let's get myself to initial amount of moles there too. Okay, so these are my initial amounts of moles. It's going to react in a 1-to-1. So whatever HNO3 reacts, the same is going to react in KOH. So my change is going to be the smaller of the two. So in the end, I'm going to have none of this. And then in this one, I'm going to have that much. Then I'm going to add the same amount because it's all a 1-to-1 ratio. Okay, so I know the amount of water in moles. That answered one question. What's the concentration of H plus or OH minus in excess after the reaction goes to completion? So I have no HNO3 left. So that source of H plus is totally gone. So for now, let's go with that answer. So this is going to be 0 left in excess. And then OH minus ions comes from KOH. 0.0, just 1 0. 1,261 moles left in excess. There we go. So this is a really good example of the beauty of an ice chart. It keeps all of your numbers organized. It keeps your thoughts, logical and linear. And in the end, you figured out multiple things. So if they're asking you multiple questions, you've got your bases covered. You definitely don't have to use an ice chart here. But when they start throwing like numbers for lots of different things at me in a reaction, I like to go into an ice chart just because it keeps me so organized. Okay, we have lots of different reactions we can do here. And actually, I want to go through one more of these as a class, and then the rest of them I'm going to kind of leave, especially this page. I'm going to leave this page for you to do because the answers are down here. If you want to take a look and try some of these and then bring your questions to me. We can also go through some of these examples together in our office hours as well. So try a couple of these, try your book problems. You can now go through the math, through the titration section. So all the like dilution, solution stoichiometry, titration, you can do all those problems now. And bring your questions to me so we can talk about those. All right, have a good night, y'all.